Welcome, everyone. Thanks so much for coming today on behalf of the Division of Analytical Chemistry of the ACS and particularly the Education Committee. I'm excited that you're here and I want to welcome you to hear our panelists talking about analytical chemistry and the opioid crisis. We have three experts with us today. Cole Altomar-Jarsik, who is at Brandeis University and uses IR for drug checking. Maria Lieberman from the University of Notre Dame, who works on fentanyl test strips, and Haley Birkland from Restec Corporation, who's an application specialist in chromatography of opioids. Let's welcome them, and Maria, I'll turn it over to you. Thanks.
That's great. Thank you, Michelle. And let me just, before we start, I just want to point out that we're recording this discussion in case there are people who want to see it asynchronously. We're expecting to do a rather short 6 or 7 minutes for each panelist, and then leave plenty of time for questions and answers. And so if you have any questions at all about the opioid overdose crisis in the US, and particularly about the role of analytical chemistry and analytical chemists in helping to alleviate this crisis, please drop them into the chat window. You can do that at any time. And David Bell will sort of collate the topics, and we'll try and answer those questions. We also have a resource folder. So it's at this http:// tinyurl address. This will take you to a lot of information from JCAM Ed and other resources about the opioid crisis, things that might be useful in a classroom setting. So I guess we will begin. All right, so this sort of sums up the opioid crisis in the United States. And what this is showing is a graph of opioid overdose deaths as a function of time. So the gray line shows all drug overdose deaths. And then underneath it, there are colored lines, and these colored lines represent deaths that are attributed to particular classes of drugs. And so this is data from the Center for Disease Control. And the thing that's really notable is starting in about 2016 or 2017, there was this rapid increase in deaths attributed to synthetic opioids, such as fentanyl. And this really kicked off in 2019 through 2023, and shows that the synthetic opioids are driving the overdose crisis. I'm going to change the slide, and maybe Haley, would you like to explain sort of the opioid structures and chemistry that you're showing in this slide?
Yeah, sure. So this is a graphic that I really like to kind of show the difference between various subclasses of opioids. What most people are familiar with is going to be the first class here, and that includes things like morphine, codeine, oxycodone. So some of them, naloxone, some of the more common opioids we hear about. And then also things like loperamide, which is a different subclass, but it is actually not something we would typically think of as an opioid. It's actually used as an anti-diarrheal drug. You'll find it in store like drugstores as Imodium, I think is the brand name for it, but it actually works very similarly to an opioid, and we see it involved in opioid overdose cases pretty often. And then fentanyl, I'm pretty sure everyone here has heard of fentanyl at this point. Those are really their own specific subclass, and we've seen a huge increase in different fentanyl analogs in the last several years. And then we also have methadone and methadone analogs, and then tramadol and tapentadol, which are kind of their own specific subclass.
All right, great. And as we'll see, these different classes really impact the analytical techniques that that can be used in order to detect the drugs. So I am going to now pass this off to our first panelist, who is Cole. And Cole is talking about a particular application of analytical chemistry for drug checking, and will let him give that introduction. So.
Sounds good. Thanks, Maria. Hi, everyone. I'm excited to chat today a bit about IR spectroscopy as a tool for harm reduction and limitations, considerations for using IR for drug checking services. So first to share, the FTIR in particular has become a particularly common instrument used in point of care drug checking settings, whether it be at overdose prevention sites or syringe service programs. They are very useful and common. And part of the reason they are so commonplace now is because they're quick. We're able to scan a sample in about 15 to 30 seconds. There's no prep work needed. The instrument itself is quite mobile. Different versions have different capacities to be broken down and moved. But as a tool for harm reduction, the FTIR did originate as going out to different music festivals and testing samples at music festivals. So folks were able to kind of be met where they were at and have their samples tested rather than having to go to a particular location where the instrument has to reside. And then lastly, for FTIR it is non-destructive, which is particularly helpful because we can either take the sample that was not destroyed and send it off for further analytic testing, either to the lab, or we can do some test strips with it, run some fentanyl test strips or other point of care drug checking tools that we have available to us. So it's it's a great instrument and robust in all that in those ways. In terms of IR in particular, it does focus a little bit on the bulk components that are in a particular sample. So if we're looking at a pill, we're not going to typically see the primary active component. We will typically just see the binder or filler, which is one of the limitations, which I'll get to in just a second. But with other samples where it might be primarily methamphetamine or primarily cocaine, the FTIR does an excellent job in being able to identify those components. But it does kind of do a bulk component detection. Next is a little bit about anyone's ability to learn and interpret spectra. Even though I came out of undergrad with a chemistry degree, I had to relearn and really focus on FTIR analysis and also learn specifically what drug spectra look like and kind of pick up on that those patterns for particular substances and get used to that. But I've been fortunate and able to train about 30 or so folks at various SSPs across New England on how to scan a sample on an FTIR and interpret it and provide those results to folks. And at the beginning of the slide, I mentioned how the FTIR and IR spectroscopy in general has really become common across the drug checking and harm reduction community. It's allowed for a really amazing support network, both within the US and internationally, that we can draw on for when there's new substances. This particular sample spectrum looks very odd. Has anyone seen this before? It's a great network that we have available to us. And next, I would like to talk about the limitations for IR. So the most common limitation that you'll hear when you're talking with folks who do this work is the limit of detection being a very problematic part of FTIR or IR spectroscopy in this particular instance, because as I mentioned, when we're dealing with pills, we typically see the bulking or inactive components that aren't really of interest. They're just used there as filler or as a method to carry the sample to where it needs to go. But also with particularly potent samples or substances like fentanyl, they can frequently be in a sample below a 5% relative concentration to the overall makeup of the sample. So there could be fentanyl in a sample, it might be at 2%, and we just have no ability to see it on the IR because we're not doing any workup and we're just looking at the sample how it is. So that's kind of the major limitation, is missing substances that are physiologically significant, but are below the limit of detection for the instrument that we are using. Next are complex mixtures. Although complex mixtures alone aren't a problem. It is typically more difficult for technicians that are a bit newer to be able to confidently identify particular substances. I'm going to show a sample spectrum that is a mixture of 6 or more components, but because we are looking at one sample spectrum, it's going to have the peaks overlaid from all those different substances that are present, and it could become very messy because we're not doing any sort of separation on our sample. Two other notes for limitations is we are not dealing with well-synthesized compounds. Frequently, particularly thinking of fentanyl, it is illicitly manufactured, not diverted. So we're typically seeing precursors and byproducts with the fentanyl as well. So we're seeing fentanyl and the other components that are in there that might be structurally very similar, and it can impact our analysis. And then lastly, the drug supply is constantly changing. Maria mentioned the uptick in fentanyl-related overdose deaths starting in 2017, but since then there have been other classes and other substances that have come along, and the drug supply is frequently changing, so we have to stay up to date with our libraries in order to accurately and confidently identify the substances in a sample against the reference library or reference spectrum that we are comparing against. So those are a few of the limitations of IR. And next, I am going to show just one reference spectrum for fentanyl hydrochloride. This is the reference spectrum that we compare against. As you can see, right around 1660 wave numbers, there is the largest peak or most abundant peak on the spectrum. So frequently, because fentanyl is not going to be our most prevalent component in a sample, the relative height of all these peaks compared to the overall sample spectrum will be significantly lower. So we are typically looking at the most unique or the tallest peaks in a spectrum to assist in our analysis. So in this instance, the peaks around 1660, the peak around 700 are kind of a couple of the peaks that we look for, but we're typically not able to confidently see all the other peaks in the fingerprint region on our sample spectrum because we have multiple other components present, inactive or active, that can kind of swamp out the view. So I just wanted to show this fentanyl reference spectrum. And then lastly, because of all the training we have done, we have referred to the 1660 peak and the smaller peak right around 1600 as the lobster claw, because we are up here in Massachusetts. And then next slide is just that sample spectrum that I wanted to show. I apologize if it's a bit small, but the red is a sample spectrum from a sample that was recorded. The purple is the composite spectrum that is trying to appropriately weight 6 different components that were identified in the sample. So in descending order, we had heroin, caffeine, fentanyl, mannitol, procaine, and xylazine. All of those components and more were identified in this particular sample, but we had to appropriately weight them to be able to see the different components and how the overall makeup of the sample can be accounted for on the sample spectrum. So I will pause there, but yeah, excited to answer any questions about IR spectroscopy. Thanks, y'all.
Great. And if you have any questions about IR spectroscopy for Cole, just pop them into the chat window. And I would like to now shift to a discussion of the lateral flow immunoassay test strips. And here's an example. So this is a fentanyl test strip, and I'm going to test a sample right here and now. So this is my sample. It's just water. So hopefully there won't be any fentanyl in it. So I'm just dunking the strip in there, and the sample is going to be tested on that strip right now. So you hold the strip by the blue end, and you dip the end with the wavy lines into the solution that you want to test. And this test is specifically developed in order to detect fentanyl. So I'm drawing the fentanyl molecule here, and I want to just point out there's sort of a core which is formed around a piperidine ring, and then there's 3 arms on the fentanyl test strip, or on the fentanyl molecule. There's the phenethyl group, a carbonyl group, and an aniline group, and these will all be relevant when I talk about the antibody and how it works. So this test strip is already giving a result. Normally we wait about 3 minutes, but you can see there's 2 lines, and for this assay, which is a competitive assay, two lines means that this is a negative result. Okay, so that's a relief to me. My lab water doesn't have fentanyl in it. But how does this actually work? And how is it used in settings outside a lab? So the test strip is used to test solutions, but the samples that people want to test usually are solids. And so solid drugs, first we have to do preparation of the sample. And anyone who's doing analytical chemistry knows that sample preparation is a really important step in any analytical method. So if you have a solid sample, it has to be converted into a solution, but first you need to know that you have a fairly homogeneous solid. And so if you're testing a tablet, you have to crush it. If it's powder in a baggie, you have to mush the bag and sort of squish the powder around to ensure that whatever you're testing is a representative of the bulk material. And then, as we'll see in a minute, there's the fentanyl test strips are specific for fentanyl, but it's also important that the sample you're testing is dilute enough that you don't get off-target binding to anything else. So let's take a look inside a fentanyl test strip. Okay, so here's a fentanyl test strip. The strip itself is just made of different layers of paper and plastic, and we can peel off the plastic at one end of the strip. So I'm just peeling that off. And inside you can see that kind of pink color there. That is a little pad called the conjugate pad. And on the conjugate pad is the red substance that acts to detect the fentanyl. So that red substance is actually gold nanoparticles that are sitting there in the conjugate pad. And then further down on the test strip, there's the absorption pad, and that has some buffers in it to help the antibodies bind right. And then further up on the test strip, there's a little piece of nitrocellulose, and that nitrocellulose has some antibodies deposited on it. So this is shows that what's going on kind of chemically. So the absorption pad is where the sample enters the strip, then it picks up this conjugate, and the conjugate contains what's called a hapten. So the hapten looks like fentanyl. So for example, up here, type B here, that's an example of a hapten molecule. And you can compare the structure of this hapten to the structure of the fentanyl molecule, and you can see it's just a fentanyl molecule, but instead of having this phenethyl group, the phenethyl group has been extended, oops, and then it's attached to this wavy line, which is a big protein like bovine serum albumin. And when you present the hapten to an animal's immune system, it will grow an antibody against many antibodies against that hapten. So the hapten is attached to the gold nanoparticles. And then these anti-fentanyl antibodies are attached to the nitrocellulose membrane. So you got to think, if there's no fentanyl present, what will happen? Well, if there's no fentanyl present, the anti-fentanyl antibody was developed specifically to recognize the hapten and bind to it. And when that happens, the gold nanoparticles will be bound to the anti-fentanyl antibody, and you get a red line there. Okay, and then there's another antibody further up the nitrocellulose membrane that recognizes a different part of the conjugate, usually the bovine serum albumin or other big target protein. So you always get a red line there. But what happens if there's fentanyl? Well, if there's fentanyl, now there's competition. So instead of binding to the red nanoparticle with its fentanyl imitation, now the anti-fentanyl antibody can see real fentanyl. And in that case, the real fentanyl, which doesn't have any color, binds to this antibody, and it blocks the binding of the red conjugate. And that's why one line means you have fentanyl, and two lines means you don't have fentanyl. Okay, so that's what's going on inside the fentanyl test strip. And now I want to also discuss an important limitation of fentanyl test strips. Okay, so the this test strip is a really great tool for doing analysis of solutions outside a lab setting because the limit of detection is so low. About 200 nanograms per milliliter is the limit of detection. And but the problem is that there's a lot of common drugs and cutting materials in drugs that can give false positives. So this is a little picture showing a bunch of test strip results. In these test strip results, the control line is on the left and the test line is on the right. So remember, 2 lines means that you have a negative result, and 1 line means you have a positive result. And so what you can see is that at low concentrations of drug, you can always see 2 lines in all of these strips. But at high concentrations of the drugs, if you have 10 or 20 milligrams per milliliter of certain drugs, like for example, diphenhydramine, which is the active ingredient in Benadryl, then you have to look really, really hard to see whether there might be 2 lines there. To many people, that those results look like positive results for fentanyl. So yeah, so fentanyl test strips have to be used correctly in order to be valuable outside a lab setting. All right. Okay, so I'm going to move on now to we have to get out of the field setting and talk about what happens when samples are sent to the laboratory. And for that, Haley is going to pick up the thread there.
All right, so I'm gonna start off by touching on how the opioid epidemic has impacted forensic laboratories, and then also get into what a huge role chromatography plays in us understanding and combating the opioid epidemic. So forensic laboratories have been hugely impacted by the opioid epidemic in the last 2 decades. For postmortem toxicology labs, it is their job to analyze samples of biological fluids from death cases to determine if drugs had any role in that death. And as opioid abuse and overdoses have increased in the last 2 decades, the number of samples that they have to analyze has also gone way up. So labs performing DUID testing are also seeing a similar increase in opioid positive cases that they have to analyze. Drug chemistry laboratories also test for drugs, but instead of dealing with biological fluids, they're trying to identify seized drug evidence so that possession, distribution, manufacturing of illicit substances can be properly prosecuted. And the data that these forensic laboratories generate is a real-time snapshot of what the illicit drug landscape looks like. It tells us exactly what kind of drugs people are using. It tells us if there's a new drug or a new combination of drugs that we need to be looking out for and adding to our analytical methods. And it also helps to paint an accurate picture of just how widespread the opioid epidemic is. Next slide. So the opioid epidemic has influenced the way that these forensic toxicology and drug chemistry laboratories run. With such a drastic increase in sample volume, laboratories are having to compensate by being able to test more samples in less time than they have previously. And so most forensic toxicology laboratories are going to start out by screening their samples by some sort of immunoassay technique, and that's typically going to be ELISA. And this is a multi-drug class screen that does not provide compound-specific results, but it will rather indicate what drug classes a particular sample might be positive for. From there, samples will undergo some sort of sample preparation technique. That's typically SPE, LLE, dilute and shoot. And the method of sample prep depends to some degree on what sort of instrumentation is going to be used for the confirmation and quantitation work. And that's typically either LCMS or GCMS. So up until probably the last decade, all quant confirmed testing was performed almost exclusively by GCMS. but we are seeing this industry largely move towards LCMS now for several reasons, but one of them being that the sample throughput for drug testing is generally a lot higher on LCMS than it is GCMS. And as I mentioned earlier, the opioid epidemic has made it so that these labs need to be able to run more samples in less time than ever before. So LCMS is an attractive option over GCMS in that respect. Next slide. So let's discuss some of the differences in forensic toxicology testing when we're using GCMS versus LCMS. GCMS requires that the compounds need to be volatile and thermally stable, which sometimes requires a dreaded derivatization step. But for LCMS, compounds don't need to be volatile. So that means that we don't have to do that derivatization step. And we also have way more drugs that are just directly amendable to that instrumentation. LCMS is also more sensitive than GCMS. And this is really important in terms of drug testing, as a lot of compounds are detected at really low levels in biological fluids. So we need that low sensitivity limit to be able to pick those up sometimes. LCMS does require an isotopically labeled internal standard to kind of combat matrix effects. And that can get expensive. That's not something that we see as much with GCMS, but my opinion would be that this is kind of a small compromise to make when you compare all the other advantages that LCMS prevents for drug testing lab work over GCMS. Next slide. So where does chromatography fit into the opioid epidemic? Chromatography is responsible for separating all of the components of a mixture. In forensic toxicology, that's some sort of biological fluid and one or more drugs. In drug chemistry labs, that's often a binding agent or a cutting agent in a mixture of drugs. And whether you're using GCMS or LCMS, let's consider how a mass spectrometer works to identify those compounds. A really basic explanation being is that it relies on a unique structural difference, unique structural differences that translate to a different mass to charge ratios, and then those are used to identify specific analytes. So the more similar in structure any two compounds are, the more difficult it becomes for the mass spectrometer alone to be able to physically separate out structurally or to differentiate between compounds. So that means we really have to rely on chromatography to be able to physically separate out those structurally similar compounds. If you look at these 6 structures here, these are 6 completely different opioids. But when you look at their structures, you can see they are really, really similar. So without an appropriate chromatography method to separate these, the chance of the mass spectrometer alone misidentifying one of these and then leading to invalid quantitation really increases. Next slide. So just to drive home the importance of good chromatography, let's talk about some of the implications that misidentifying a substance would have. Inaccurate reporting can mean a missed cause of death or an inability to prosecute a drug case. It can mean differentiating between a perfectly legal prescription and someone that is using a drug illicitly. It also is important because accurate reporting helps us understand the illicit drug market trends, seeing what drugs are most prevalent, if there's any new compounds emerging. And for scientists working in this field, they're really looking at every case they touch, every analytical method they develop with a lens of, I might have to testify about this in court eventually. So they need to be able to go up on the stand as an expert witness and be able to say, we can be confident in these results because the science behind my test methods are solid. I can say with a high degree of certainty that this drug is what I identified it as, and here's why. And that really can't help it or cannot happen without good selective chromatography methods.
All right, well, we have come to the end of our sort of prepared remarks here. And now what we are hoping to do is to collect some questions from the people who are watching this panel, so we can have a little bit of back and forth. So yeah, so I'm gonna ask, I saw there's one question in the chat from Pritha, and maybe we can talk about that. But while we're doing that, please think about if there's any questions you have about the opioid crisis, about analytical chemistry in the opioid crisis, please drop them into that chat window. So David, do you want to sort of run the Q&A?
Sure, it's like you said, we have one question from Pritha asking, since fentanyl is a controlled substance, are there procedures to follow and to work with them, I assume other controlled substances in university settings?
Well, I'm somebody who is a university laboratory, and I work with controlled substances. So my lab we went through the process of getting registered with the DEA to handle controlled substances, but for all controlled substances, there are different levels of concern that DEA has about the substances. And so there's a recognition for the benefit of people being more widely able to work with, for example, reference standards. So if you want to work with reference material for a substance such as cocaine, so there's some great analytical experiments that you can do with a GC extracting cocaine off of currency. And the reference material for that is not a controlled substance you can buy from Sigma. And so there's sort of there can be sort of intermediate stages if you're interested in working with an opioid substance or stimulant substance in an undergraduate lab class, for example, then there are some ways that can be done that are safe and that are legal to do.
There's one mention that you can't hear me. Can you hear me now? Or you can hear me okay?
Yeah.
Yeah. So, Michelle asked, what's the most important analytical problem still facing the opioid action?
Maybe Haley, you want to take a crack at that one?
Yeah, sure. So I would say one of the biggest issues that analytical labs are still facing is kind of keeping up with all of the new compounds that are emerging. If you keep an eye on novel psychoactive substances, we see a new compound coming out pretty much every week at this point. So, and that's something that illicit drug manufacturers are doing on purpose to kind of skirt drug scheduling guidelines. So if you think about fentanyl analogs, those were scheduled by the DEA in a way that they pretty much scheduled anything that was a fentanyl analog, or basically had that core structure. So that kind of applied to drugs that maybe hadn't even been, or fentanyl analogs that maybe hadn't even been manufactured yet. They were just kind of trying to take that out all in one sweep. So as a response to that, we see the illicit drug market turn to other sorts of synthetic opioids. The most popular one right now are called nitazines, and they have similar potency to opioids, but the structure is different, so they don't fall under that scheduling guideline, and they aren't technically illegal then. And we see that happen with all drug classes, from opioids to stimulants to synthetic cannabinoids. But it's a lot of work for toxicology, drug chemistry laboratories to keep their scope up to date, knowing what is going to be popular basically on the drug market. I would also say, I kind of mentioned, all of these are really structurally similar, and that means lots of isomers, lots of isobars that are going to have the exact same chemical structure, but are technically different compounds, aside from one double bond or the location of one functional group. And separating those out by chromatography can definitely get really challenging.
Great,
Cole, do
thanks,
you
Andy.
have any comments on that? Because I think you're coming at this from a very different angle. So,
Yeah, I'd love to speak to that specifically with the differences in potencies, even across just the class of fentanyl and fentanyl-related analogs. It's extremely important to identify which particular substance it is, whether it's traditional, what we consider traditional fentanyl hydrochloride, or is it carfentanil, is it acetylfentanyl? And that is one other limitation that I didn't get into too much on limitations of IR, because we are frequently dealing with fentanyl or super potent opioids in very small concentrations relative to the overall makeup of the composition of a sample. It can be, we typically report it as fentanyl or fentanyl analog. We typically don't have sufficient matching to differentiate between fentanyl and analogs via our point of care testing instrument. And that is another major limitation, and it is tough. And as Haley mentioned, the increase in nitazines is, it's tough for some libraries to be as up to date as the drug supply is. So just reiterating that and that out there as well.
Great, thanks, Cole. So speaking of libraries, one other question here is, are databases being created for LCMS and S spectrum for specific drugs?
So yes and no. Just typical LC triple quad MS instrumentation is actually a targeted approach to quant confirm. So they actually don't operate with a database library situation like you would expect with GCMS. You are putting very specific transitions, analyte settings into a table, and then the LCMS is using those transitions to look specifically for those drugs. So if you don't have that analyte in that MRM or SRM table, you won't pick it up. You won't pick up anything but those. But we are seeing some labs start to use LC coupled to some kind of high resolution mass spectrometer. So a QTOF or an Orbitrap, something, and those use more of a library-based approach. So they are collecting databases full of spectra, and those are becoming available for labs to use. And it's pretty easy for them to add new compounds into that library in-house. So they can kind of grow their own database based on what they see, what they are anticipating will become a popular drug in their area.
and I should say that that there's a group at NIST, the National Institute of Standards and Technology, that work on illicit drug analysis. And so they have been pretty active in sort of sharing information on these sort of non-targeted databases for people who are doing the both high resolution, but also unit mass resolution untargeted analysis.
If I can add something, the standardization of how you acquire those MSMS libraries is hugely important to an accurate database. We don't have the same control over it as we do in GCMS, for example. Great, thank you very much. What other techniques are used or could be used in addition to IR, LCMS, and GCMS? What are we missing?
So I think near IR is very underused. So near IR is a cheaper technique than FTIR, but it's extremely library based. And so far I haven't seen any good libraries for illicit drugs. And there's been some work with portable Raman instruments. So there's a device called the TrueNarc, which is being used by police departments. And that also is really dependent on the utility of the device is very strongly dependent on its library and how the operator is using the device.
One technique that none of us mentioned was also color testing. That's a very common procedure done in drug chemistry testing laboratories. And it's very simple. It's typically using a marquee reagent that you apply to a spot of suspected drugs, and then based on what class that drug is from, whether it's an opioid, if it's a stimulant, methamphetamine, it will react a certain color, and then the analyst can then use that result as kind of a screen for the confirmation panel.
Good. And speaking of screening, one other question here is fentanyl test strips can only be used for screening, but not to confirm, since other drugs can give false positives.
That is
Expressed as a
absolutely
question.
true. Yeah, the fentanyl test strips are a presumptive testing device. They are useful as warning, but they should not be used as a confirmatory test. Yeah,
And-
because you
and
can get
just-
false positives.
and this is actually for Cole, I was wondering, as you were speaking, how often when you get a positive test, do you have to send samples out for something that's confirmatory with the IR testing? And what is that? That's
Sure.
usually-
Yeah, I can speak to that a good bit. Currently, with our process, because of the considerations for the limitations of IR and the drug supply that we frequently have is so messy and complex, it's really important for us to be able to send off most, if not all, of our samples for further testing to identify the substances that are in there in very low concentrations, but are still physiologically significant. So we do have some recommended procedures in place if we're not able to send off all samples for laboratory testing. It's typically samples associated with a negative health event, or had an extremely odd or adverse reaction, and then also random choice or random selection from there on, so that we can continually see kind of what's being seen from the lab testing, since it is a bit more sensitive and able to see those components in very low concentrations.
Thank you. Let's see. How available are isotopically labeled panels?
They are becoming more available. I kind of mentioned how often we see new or novel psychoactive substances pop up. And obviously, nobody can test for those until there's a reference standard available. So there's only a few different groups that synthesize these compounds and put out reference standards for them. So the first priority is always kind of putting out a reference standard for that specific new analyte. And then hopefully a few months later, they will come back and release an isotopically labeled version of that analyte that can be used for quantitation.
I mean, one thing that helps a little is that the quantitation, at least for, I guess it depends on the application, but for some applications, the quantification doesn't have to be to within 5%, right? That when, yeah. Yeah, the availability of reference materials is an issue because it's expensive. And so if you've got a long list of targets that you're trying to go after, and a reasonable list of targets these days might be 50 to 80 compounds. If you're trying to detect some of the novel substances in addition to sort of the bulk drugs and the cutting agents. And that can start to run into a fair amount of money. So. Question for me about collaborating with harm reduction organizations. So for example, I got interested in these fentanyl test strips. We obtained a whole big batch of fentanyl analogs through a program that CDC runs. They prepare these what are called traceable opioid materials, reference materials, or TOMS kits. And so we were able to just run all those fentanyl analogs on the test strips, and we could see that different brands of fentanyl test strips were using different antibodies and different haptens on the strips. And so it was like they had different blind spots. So some of them could detect, modifications to the phenethyl group, and others could detect modifications to the carbonyl group, but usually they couldn't detect both. So we were interested in that, and we have also started looking at the fentanyl test strips as a way to, like if you have a result on a fentanyl test strip, that came from a certain sample, and that sample is still sitting there on the test strip, right? Because you dunk it in the solution is now dried on the paper of the test strip, and so it's possible to then soak that in a solvent and extract all the other drugs that are present in the sample and do some analysis on that. So, so we've been interested in doing that, both to back up, like if someone gets a weird result on a test strip, we can sort of do try and figure out what happened, what might have gone wrong. And then just for general monitoring of what's going on in the community, in terms of the illicit drug supply. Because as Haley mentioned, right, we're seeing new substances entering the drug supply on a weekly basis. I don't know, what are some of the substances that have been popping up in samples you've been looking at recently?
Is that an open question to anybody, or
Yeah,
anybody thinking?
anyone who's working with illicits, I guess.
I haven't been working on casework for a little over a year now, since coming to Res Tech, but I saw all sorts of a really huge variety of drugs, working where I was at, which was in central Pennsylvania. And something that's important to understand is that the drug demographic looks different from place to place. Places like Florida or Tennessee, like Nashville, we see a lot more designer drugs compared to places like Pennsylvania, West Virginia, where we're going to see more things like methamphetamine, fentanyl. I definitely saw tons of that. We would occasionally see nitazines. We would see some synthetic cathinones like Utilone and Pentalone every once in a while. So it's definitely a huge mix.
Someone asked a question about other techniques, analytical techniques that are used, and I should mention that when there's a completely unknown new psychoactive substance, that sometimes techniques like NMR, the classic structure elucidation tools, can be really, really useful in figuring out what that new substance might be.
So unless I missed something, I don't see any more questions online. If you have any, please feel free to type them in.
Okay.
Well, I actually have one more question for you. So a lot of our techniques, even mass spectrometry, we're trying to get miniaturization, trying to mention point of care kind of reference. Okay. Are the same things happening with IR? Are we trying to get smaller and IR on a chip, IR on a cell phone, that sort of thing?
Yeah, actually, I can speak to that a bit. There are a new kind of realm of Raman instruments that are really kind of being offered as like handheld. So in theory, the person themselves could use the Raman instrument and receive the results for, rather than having to go to a drug checking technician at an SSP and get their samples checked. So there is that work. There's also quite a few other efforts that are being done. For example, a group up in Vancouver, they do have, I believe it's a not an LCMS, but they have a laboratory grade instrument in their SSP. So that is another.
It's an LC, it's a tandem instrument, so tandem mass spec with an LC on the front. So that's the substances drug
Thank-
checking place. Yeah.
Thank you, Maria.
Yeah.
Yeah, so there's some efforts to make kind of like the traditional laboratory techniques available in kind of point of care settings, but there's also all these efforts to kind of create new versions of the technologies that already exist to be able to be more mobile, or able to be operated by someone who doesn't necessarily have their master's in chemistry. So there's various efforts being done, but one of the most important bits is the testing of samples outside of the laboratory setting. So really getting practice and real world samples to validate those procedures, and the results reported by those new technologies is one major difficulty.
Don't see anything else online. Michelle, did you have anything you want to say?
Okay, well then I think we'll wrap this up, and thank you all for attending. And if anybody has any questions, feel free to just drop an email, and I guess we can follow up through the DAC ChemEd group. We'll make the recording available through that same mechanism, and we'll circulate the link to all the resources for this panel. So thank you for attending.
Great, thank you all.
Thank you very much to all our panelists.
I'm going to turn the recording off now.
Thank you. Take care.